Welcome back, everybody. So we're going to be looking at equations 7, 8, and 9 here, which are going to form the last two groupings of graphs that we look at, and then we'll look at one particular other one that'll be kind of interesting called the Archimedean spiral. So for number 7, we've got this graph that looks sort of like a circle graph. So prior graphs that we had, so like r equals sine theta, this would just be a circle with a particular symmetry. So for this one, though, the difference is that we're now multiplying the angle, which kind of implies there's some sort of dilation going on here. So we're going to inspect here with some points and see if we get a different graph than those normal circle graphs. Now, obviously, this won't be a Limassol because we're not adding some quantity to it. So this is going to have kind of its own particular form. So we'll note at 0, well, sine is just 0. So we're going to start at the pole as our initial coordinate. And maybe we'll look at pi over 6, since that's a nice angle measure typically for sine here. And we'll see that we're going to have to multiply it by 3 here. So this is going to be 2 sine of pi over 2 then. So I'm going to be a little extra careful here and write out the coordinates. So at pi over 6, we're going to be at 2. So we'll note from 0, or maybe even just to be a little bit more careful. So that's going to be kind of the first part. So from 0 to pi over 6, we start at 0 and then we rotate towards 2. Maybe we'll look at pi over 3. That might be interesting because that'll give us 2 sine of pi. But sine of pi is just 0. So that means by the time we reach 60 degrees, we're back to 0. Okay, so this is definitely not a circle, definitely not a Limassol or cardioid. So we've got this first little shape here. And so let's keep going. So at pi over 2, we'll be at 2 sine of 3 pi over 2. But 3 pi over 2 is going to be negative 1, so that'll put us at negative 2, which means at pi over 2, we're going to be in the opposite direction. Okay, so let's go ahead and keep going here. 5 pi over, actually, let's do 2 pi over 3 first. So 2 pi over 3 is going to give us 2 sine of, 6 pi over 3, which is 2 pi. So that's just going to bring us back to 0. So that means from pi over 2 to 2 pi over 3, so there's a, sorry. So we'll note, so we rotate around, and then we go back to 0 again. So we'll keep going here. So we'll go to 5 pi over 6. So at 5 pi over 6, we're going to get 2 sine of 5 pi over 2, which is the same as pi over 2, which puts us at 2. So at 5 pi over 6, we'll be back at 2. So we're going to keep this kind of symmetrical rotation going, and we can kind of see what our endpoint is going to be. So our endpoint is going to rotate back that way, which is going to be at pi. So once I reach pi, I'll go back to 0. So it only takes pi here, and then we're just going to continually rotate around this. So once I go back to the original, I'll rotate again around, and then repeat again. So note, we're going to have kind of this repeated rotation about the axis that's going to retrace this graph. And so this graph we can see has some petals to it. These should be symmetric, so my graphs are not exactly right, but graphing this on Desmos, you'll see how beautiful these graphs really are. So this is what we call a rose curve, and each one of these pieces here are called petals. And we'll note those coordinates. So we've got 2 comma pi over 6. We've got 2 comma 5 pi over 6. And then we've got negative 2 comma pi over 2. So those are our 3 maximal points here. So you can see that the maximum point is going to come from that lead coefficient, because obviously sine is going to be between -1 and 1, so it can't be any larger than 1, which means that the maximum or minimum values can only be at most plus or minus 2. And the pi over 6, the 5 pi over 6, and the pi over 2, you'll see are values that give you the maximal value of sine 3 theta. All right, so if you look at when sine 3 theta equals 1, we'll get theta equals pi over 6, 5 pi over 6, and then repeating. Or when we're minimal, -1, we'll get theta is equal to pi over 2, etc. And so those maximal values where we are at plus or minus 1 are going to be where the petals are furthest from the origin or the pole. All right, so 8 is another type of rose curve. And now we've got 2 cosine 2 theta. So we've got a cosine graph, and now we're doubling instead of tripling the angle. So go ahead and take a moment, maybe pause, make a theta R table, and sketch the graph of this. Let's see what it looks like. So I will make my theta R table here. We'll start at 0, which is obviously going to be a maximum value because cosine of 0 is 1. So we're going to start at 2. Then we'll go to pi over 6 again, maybe, because that'll give us 2 cosine of pi over 3, which is 1/2. So that'll be at 1. So at pi over 6, we're at 1. And then pi over 3 is going to be not a nice value. Let's try pi over 2. So that'll be 2 cosine of pi, which is going to be -2. All right, so we'll note our initial point here is going to end up back at 0. Now we should probably maybe point out where that's going to occur. So that's going to be at pi over 4. So 2 cosine of 2 times pi over 4 would be pi over 2, which is 0. So that point is going to be pi over 4 where we go back to 0. And then from pi over 4 to 90 is where we're going to rotate here. Let me try and get that somewhat correct here. So we can see the petal is already beginning to rotate out here. But now we're not going to be curving a particular petal at once, right? So we've started with one petal and it looks like we're moving into another petal. So at 5 pi over 6, we'll have 2 cosine of 5 pi over 2. Sorry, 5 pi over 3, which is going to be 1/2. So we'll be back at 1. Sorry, yeah, 1. So at 5 pi over 6, we'll be at 1. Okay. Oh, and I see I've forgotten the 45-degree angle. Should have done 3 pi over 4 first. So that's going to be 2 cosine of 6 pi over 4, which is 3 pi over 2, which is 0. So we're going to trace quickly back to 0. And then we're going to rotate out from 5 pi over 6 to pi, which will be 2 cosine 2 pi, which will be at 2. And now we can kind of see how our rotation is going to work here, but our picture does look a little different. So maybe we'll keep plotting points here. Because note, we're not done yet like we were with the 3 theta. So we'll do 4 pi over 3, which would be 2 cosine of 8 pi over 3. And 8 pi over 3 is the same as 2 pi over 3, which is going to be -1. So at 4 pi over 3, we're going to be at -1. And I'm missing 5 pi over 4 in between, so which will be 2 cosine of 10 pi over 4, which is 5 pi over 2, which is 0. So again, very quick rotation back to 0. And so at 3 pi over 2, we're going to be -2. So we're going to rotate this way. And completing our rotation, we will finish our rose curve. So again, which we could get by plotting all the way to 2 pi. But for these, once you kind of see the symmetries with certain points, these will be pretty easy to trace out. And again, then it'll continue to trace itself out. So note, as we're tracing it, it's going to always trace in the same direction. So again and again. And again, we get another rose curve. But we don't have 2 petals. So now 3 theta has 3 petals. But 2 theta has 4 petals. So this is going to be a common theme with rose curves, which is if we have r is equal to a sine b theta, let's say, if beta is odd, and we have odd petals, whatever that number is. If beta is even number, we're going to have 2 times the even number of petals. So really cool graph. The graph would be like r is equal to something like 2 sine 4 theta, which is going to have 8 petals, or 8 theta, or 16 theta. So you'll see quickly how cool and interesting these graphs can get. So the last graph that we're going to look at is this r squared equals 2 sine 2 theta. We'll just note the name of this one is called the lemniscate. But you could think of this more simply as a figure 8 graph, as you'll see by our graph that we're going to sketch in just a moment here. Now note though, we do have r squared, which is going to put a specific requirement on r here, which is that we're always going to get a positive number. So we'll want to be a little bit tricky with, or a little bit careful, sorry, with our values that we choose. So we'll start with 0. So at 0, r is going to just be 0. So again, we'll start at the origin here, at the pole. And then we'll pick, again, nice values of our angle, but that are relatively small. So we'll start with, looks like pi over 4 would be a good angle to choose, because then we'll get 2 sine of pi over 2, which is going to be 2. So at pi over 4, we're going to be out at 2. And then going to pi over 2, we'll see that we go back to 0. So very similar to our rose curve here. But what we'll notice again here is that we cannot be negative, right? We can't be negative numbers, so we need to skip over any values that make sine of 2 theta negative. So, whoops. So something like 3 pi over 4, we can't use 3 pi over 4, because 3 pi over 4 would give us a negative valued angle measure. If we go to pi will just give us 0. But 5 pi over 4 will give us 2 sine of 5 pi over 2, which is positive 1 again. So that means that 5 pi over 4, we're going to get a very similar shape here. And then we could plot to 3 pi over 2, which is going to give us 0 again. And so what we'll see is that any angle measured in the second quadrant or the fourth quadrant are going to be non-existent values of this equation, because r is required to be positive. Right? So if we're squaring r, we cannot have a negative r value. So what we end up with is this figure 8, which has symmetry, slightly different symmetry. Symmetry about the pole, which is our origin symmetry. And our last graph here is the graph r equals theta. So this is an interesting graph. So this is called Archimedes spiral. And we'll see why in a moment. So we'll note r and theta are going to match here. So at 0, theta will be at 0 r. But then as we start measuring at our angles, right, we're going to get larger and larger values. So this graph is going to look like a spiral, kind of going outward. And I'm not going to try to draw it to scale here. But note we typically do theta in radians for these. But you can do degrees as well, but then you're at 30 degrees is going to be 30 units of r. Using degrees doesn't work because r has to be a real number. So note theta is going to be in radians here. So, again, a nicer version of this graph. Let's see if we can do that. So at pi over 6, that's going to be about a half. Or, yeah, a little bit bigger than a half. At pi over 3, you're going to be a little bit bigger than 1. Pi over 2, you're going to be a little bit bigger than 3/2, so something like this. But I'll just kind of draw it in general, but Desmos does much better justice to it. But we'll note here, though, is there is no symmetry. So this is a graph with no symmetry, so they don't all have nice symmetries to them. And so if we go down here, we've got kind of the organizer here of all the different types of graphs. So we'll note horizontal and vertical lines we can write with cosecant and secant. So these will be kind of typical ways to write horizontal and vertical lines. And then lines with non-zero slope are going to be theta equals k. So we looked at when k is pi over 6 on the very first page. And then we'll note circles and spirals here. So we've got the spiral graph that we looked at, and then our two different circle type graphs, including the circle centered at the origin. And then we have all of the different Lima zones here. So we've got the inner loop, the dimpled, and the convex. Again, you don't need to memorize any of those names. And then we've got our rose curves below and lemniscates below. So these are going to be the main focused polar graphs that we look at, but there's a lot of different types of polar graphs beyond these. But these are the ones with the most interesting symmetries. So our last step here then is going to be to describe the different symmetries. So we'll stop the video here, and then we'll finish this in the third part. But note the symmetries here is going to be really, really crucial to what we do with polar graphs as well. So until I see you next time, take care. And if you have questions, shoot me an email or drop by my office hours.